So before looking at Taylor and Maclaurin series, it's important to review what you know so far about it. And yes, believe it or not, you have already done a little of this back in Calculus 1. However, in Calculus 1, you did what we call a linear approximation, for which pretty much every function, you name it, e to the x, sine x, cosine x, square root of x, cube root of x, 1 over x, ln of x, whatever function can be approximated to a linear function, and that we get by evaluating the original function plus the derivative of the function times x minus the center value at which we find that linear approximation. Alright, well, so here in this section and in this class, we're going to expand that approximation. So we're going to go beyond the linear approximation. We're going to go to the quadratic approximation, the cubic, quartic, quintic, etc. So depending on how many terms are we asked to find. Alright, so in the meantime, let's review a little bit of what we did back in Calculus 1. So we want to find a linear approximation for the function f of x, square root of x, at x equals 25, and then use it to find the value of 26.5. So the idea is to evaluate the square root of 26.5 without ever using a graphing calculator, and that's what we're going to do. We're going to use calculus and some algebra to evaluate that. Well, to find the equation of a tangent line, we need two pieces of information. One of them is a slope, the other one is a point. Well, we can find the point by evaluating the original function at 25, which is the center value. That's the square root of 25, and that result is 5. So that means the point will be 25, 5. Now we need the slope. Well, how are we going to get the slope? Well, derivative. Find the derivative of the function. First of all, f of x equals to x to the 1/2. In order to we can differentiate this function, we cannot take the derivative just like that while is it in radical form. F prime, that's 1/2 x to the negative 1/2, which reduces to 1 over 2 root of x, and we can find the slope evaluating the derivative at 25. So that's 1 over 2 times the square root of 25, which is 1 over 2 times 5, which is 1 over 10. Alright, so that's 1/10, that's our derivative. So we have the two pieces of information. Let's find the equation of the line. Y minus y1 equals m times x minus x1. Well, you know the drill from Calculus 1. You got the point, you got the slope, use the point slope form, and just plug in the information that we have. So this is our y1, this is our x1. Y minus 5 equals m, which is 1/10, x minus 25. And I know what you might be thinking, to distribute the 1/10, but don't do it, because if you distribute that, that's going to give you some trouble when estimating the value of the square root of 26.5. So all I'm going to do here is y equals 1/10 x minus 25 plus 5. And whoa, this linear approximation is to say the following. It's to say that the square root of x is approximately 1/10 x minus 25 plus 5 at the point 25, 5. Where are we going with this? Well, you'll see. Number one, let's approximate the value of 26.5. And so, oh no, that's approximately, not equal to. So 1/10 is 25 plus 5, 26.5, and that's approximately. So this means square root of 26.5 is approximately, well, 26.5 minus 25, so that's 1/10 times 1.5 plus 5, and this is 1/10 times 3/2 plus 5. But well, 10 times 2, that's going to be 20. And multiply by 20. Divide by 20 for the least common denominator. 5 times 20, that's 100 plus 3. That's the square root of 26.5 is approximately 103 and divided by 20. But what's all this anyway? Well, what's the bigger picture? Why do we review? And so number one, we review this so you can see the limitations of the linear approximation. So this is the graph of the square root of x, and let me scale this to 5, 10, 15, 20, 25, and so what did we get? We got the tangent, the equation of the tangent line at right, something like this, right? So that's the equation. Let me do this right. Sort of, yeah, sort of. So we are using this approximation, this linear approximation to, okay, let me keep going beyond, to evaluate the square root of 26.5. And in this case, well, this linear approximation is okay to evaluate that value of 26.5, because here 26.5, the difference between the actual value and the approximated value is not that big. However, the question is, can I use this linear approximation to evaluate, say, the square root of 5.1? And the answer is no, because if you look at this value right here, the actual value versus the approximated value, it's not an accurate approximation. The difference between those two values is going to be really big. So number one, there is a couple of options to do this. Number one, create a whole new linear approximation, but now around a value that has a perfect square root preferably, and it's close to 5.1, and that approximation we would do it at 4. All right, that's one option. The other option is to go beyond the linear approximation and add more terms. That is, the quadratic approximation, the cubic approximation, the quartic, quintic, etc. The more terms we add to the approximation, the polynomial approximation, what's going to happen? That line will become a curve, and that curve, the more terms we added, that curve will overlap more points on the original, so that's why we would be able to evaluate for other functions. Well, I'll give you a better visual of this with another example. Is it in the next page? No, not yet. In the next couple of pages. So, in the meantime, let's define what a Maclaurin series is. But by the way, I have a little typo here, and that's simply x to the n. So this is a series that we sort of looked at already. The difference here is that this fn, which represents the n derivative, that's for the number of the derivatives that we are going to need to take in order to find, a particular approximation. For example, for the linear approximation, we needed to find up to the first derivative, so that's why this n would be 1. For the quadratic approximation, we will need to find 2 derivatives. For the cubic approximation, we would need 3 derivatives. For the sextic approximation, we would need to find 6 derivatives and evaluate those derivatives at the center value. If it's a Taylor expansion, well, that's centered at some value other than 0. But otherwise, if it is Maclaurin series, which is the case that we're going to do for now, that's going to be evaluated at 0. So all these derivatives that we are going to compute are to ultimately find these values: f of a, f prime of a, f double prime of a, f triple prime of a, which are the Taylor coefficients or the Maclaurin coefficients depending on the center. So it's essentially the same, it's just the number at which we evaluate will be different. Well, you'll see what this is about. And I'm going to warn you, these problems are going to take a good minute to go because we need to write a lot. Functions, derivatives, evaluations, polynomials, you'll see. Alright, use Maclaurin series to find a power series for the function f of x equals 1 over 1 minus x. Well, this one you already know it. You know it from last week. This is sigma n equals 0 to infinity. And that's x to the n. That's actually the general geometric series. However, we are going to obtain it from by using Taylor, or rather Maclaurin series. Well, whenever they tell us Maclaurin means centered at 0. So let's go ahead and do this. So f of x, that's 1 over 1 minus x, which is the same as saying 1 minus x to the negative 1. And I need this version so we can take the derivative. You'll see. So that's evaluate the function at 0. That's 1 over 1 minus 0. That's 1 over 1, which is 1. Let's take the derivative from this version. So f prime of x. So that's negative 1 over negative 1 times 1 minus x to the negative 2 by mini chain rule times negative 1. Well, that's going to become negative x, or rather simply positive 1 over x, or rather 1 over 1 minus x quantity squared, and evaluate this to get f prime at 0. Well, that looks like a 6, 0. That's 1 over 1 minus 0 quantity squared, and that equals simply 1. 1 minus 0 is 1, 1 squared is 1, and 1 over 1 is 1. Second derivative. The second derivative, okay, this is a plus, that's going to become a negative 2 times 1 minus x to the negative 3 times the negative 1 becomes positive. That's a 2 over 1 minus x cubed. And evaluate the second derivative at 0, so that's 2 over 1 minus 0 cubed, which is in this case going to be simply 2, because 1 minus 0 is 1, 1 cubed is 1, 2 over 1 is 2. The third derivative, and we're going to stop at the third derivative. I think that's enough. That's good enough in order to find a pattern. So that's negative 2 times negative 3. That's positive 6. And 1 minus, or actually, well, if first negative 6, yes, negative 6, 1 minus x to the negative 4 times negative 1, which becomes all positives all the time, all right? 2 over 1 minus x, or rather not 2 but 6 to the 4th power, and f triple prime at 0, that's a 6 over 1 minus x to the 4th power, and that's a 0 to the 4th power, and well, that's 6. So let me do some highlights here. Let me highlight this one. Oops, no, I meant highlight. Highlight this, highlight this. Alright, so let's start with the formula. F of x equals sigma n equals 0 to infinity, and that's f, and that's the n derivative, in this case evaluated at 0 because it's a Maclaurin series, divided by n factorial x to the n power. So we're going to start expanding, in this case 4 terms, up to the third derivative. So f sub 0, or just f of 0, over 0 factorial x to the 0 plus f prime evaluated at 0 over 1 factorial x to the first power plus f double prime at 0 over 2 factorial x squared plus f triple prime of 0 over 3 factorial x cubed, and well, the pattern just goes on forever. Okay, pattern goes on forever, and let me highlight the corresponding coefficients. Well, so number 1, so this one will be this one right here. Oh, come on. This one is this one right here. This other one will be this one right here. And these two will be this coefficient here. And this triple prime is this 6. Alright. So let's just substitute the numbers. So f of x, that's going to be 1 over 0 factorial, which is 1, x to the 0, plus 1 over 1 factorial, which is 1, plus x to the first, plus f prime, which is 2, over 2 factorial, which is 2, x squared plus 6 over 3 factorial, which is also 6, x cubed, plus dot dot dot, that just goes on forever. And simplifying this polynomial, that's 1 times x to the 0, which is 1, that's just 1, plus x, and the 2's cancel, the 6 cancel, plus x squared plus x cubed. And well, we can see the pattern, sigma n equals 0 to infinity, and this is x to the n. So this is the same power series that we obtained by just using the definition of the geometric series, of the generalized geometric series in the convergence case. In the case that we have x to be less, the absolute value of x rather, to be less than 1. That's the condition for convergence. So that's another way to get this power series, not using that definition, but I mean in a more generalized way. So let's see what's next. So let's get at last a series expansion for the function e to the x. Well, so we need to find a few derivatives. 3 are fine, and again, Maclaurin means centered at 0. So let's evaluate the function f of x e to the x, f prime of x, not f prime, f at 0 e to the 0, which is 1. The derivative of e to the x, which is itself e to the x, evaluate f prime at 0, e to the 0 is 1. Take the second derivative, which is itself, it's the same unless we had a coefficient, which we will in a further example. You'll see how is that going to work later. And that's e to the 0, which is 1. And well, it looks like we're just repeating this. And yes, it's true. E to the x, f triple prime at 0, e to the 0, which is 1. It's the same thing. And well, we don't need too many derivatives in there. Just 3 are fine. And it happens to be the same coefficient. So let me highlight those coefficients. They're all 1s. Okay, they're all 1s. And let me write down the formula for f of x equals sigma n equals 0 to infinity the n derivative at 0 over n factorial x minus 0 to the n, which is just x to the n, because it's centered at 0, because it's a Maclaurin series. We'll do an example with with the Taylor series later. Maybe not today, but next time. So this is again f of 0, x to the 0 over 0 factorial plus f prime at 0 over 1 factorial x to the first plus f double prime at 0 over 2 factorial x squared plus, well, the pattern just goes on forever. Even though I did 3 derivatives, I'm just going to write a couple of terms here. I think you can see the pattern just increases. The pattern just increases by 1 unit every time. All right, so let's see about it. All these coefficients right here are 1, 1, and 1. And same for the third derivative. So this is what we're going to do. So f of x equals 1x to the 0 over 0 factorial plus 1x to the first over 1 factorial plus 1x squared over 2 factorial plus 1x cubed over 3 factorial. And while the pattern continues, notice how these evaluations at x equals 0 are 1 every single time. So we can keep writing more terms. So that's 1x to the 4th over 4 factorial, etc. Well, in this case, no need to simplify the factorials, because in this case we will need this to find a pattern for sigma notation. So sigma n equals 0 to infinity. Well, number one, it involves powers of x in the numerator that actually go between 0, 1, 2. They go by the integer sequence, that's x to the n. And the factorials in the denominator, they just go again with the same sequence of integers. 0, 1, 2, 3, 4. So we finally have a power series representation for the function e to the x. Well, I'm going to simplify the factorials in the end. You'll see why. That's because I want to make a point between the linear approximation and further approximation. So this is the same as saying 1 plus x plus 1/2 x plus 1 over 6 x cubed. And 4 factorial is that 6 times 4, that's 1 over 24, x to the 4th power. And this, of course, goes on forever. All right. In this polynomial right here, what do we have? The first two terms of this polynomial expansion would give us the linear approximation. The first three would give us the quadratic approximation that I needed to over here. And then the first 4 terms would give us the cubic approximation, and the first 5 terms would give us the quartic approximation. What's the picture here? Well, so I have the graphs of the original function and each of the approximations: the linear, the quadratic, the cubic, and the quartic approximation. So you can see how adding more terms to the approximation gives us a larger interval to use this approximation to compute certain values or certain approximations. For example, for the linear approximation centered at 0, well, check this out. Check how this linear approximation would give us a very limited interval of values, so we can use this approximation to, for example, evaluate e to the negative 0.1, e to the 1/3 maybe, up to between e to the negative 1/3 and e to the 1/3, for example. However, can I use a linear approximation to estimate the value of e to the 1st power? Do you see the difference? Do you see this big gap? Can I use it to evaluate e to the negative 1? See the gap between the actual value and the approximated value? Well, again, one option is to come up with other linear approximations near these values. That's one option. However, the best option here is to just use a polynomial approximation. What happens with the quadratic approximation? Well, I still can't use the quadratic approximation to compute these values, because there's still some difference between the actual and the approximated, especially on the right side. But it's getting better. It's getting a better approximation. Let's see what happens with the cubic approximation. Oh, do you see how this gap between the approximated and the actual value is getting smaller every time? Well, that's because we're adding more terms to the approximation. And let's see what happens with the quartic approximation. So at this point, for the quartic approximation, See how the quartic approximation is actually overlapping more points on the original function, so we can use, so that quartic approximation, we can use it at least to estimate any value between -2 and possibly even 2. I don't know what's going to happen later in the graph, but for sure it's overlapping at more points. All right. So that's the same thing that we can do over here when it came to the graph of the square root of x. So we could have created a cubic, maybe a quartic, so that it overlaps. So that it overlaps like this, and we could use that cubic or quartic to evaluate the square root of 5.1 without having to find another linear approximation. So that's one of the applications for Taylor and Maclaurin series, to estimate certain values. But well, we're also using this idea to obtain power series for other elementary functions. So let's go and find a Maclaurin series expansion for the function f of x equals sine of x. All right. So, and we're gonna do the same. The drill is the same. F of x, find some derivatives. So number one, f of x equals sine x. F at 0, sine of 0 equals 0. Take the derivative, that's cosine. F double prime at 0, cosine 0 is 1. Take the second derivative, negative sine. F double prime at 0, that's a negative cosine, wait a minute, yes, negative sine of 0, that's 0. The third derivative, negative cosine, and the third derivative evaluated at 0, that's negative cosine of 0, which is negative 1, because cosine of 0 is 1 times a negative in the front, that's negative 1. F quadruple prime, in this case we use parentheses and the number 4 for the fourth derivative, and on we use this notation, the order of the derivative in parentheses. So of x, and well, what's the derivative of cosine? First of all, that's negative sine times the negative in the front, that's going to be sine. But do you notice a pattern here? It's taking us back to the original function because of the oscillation of the values of the trigonometric functions sine and cosine. So that's a sine of that's supposed to be 0, 0, and that's a 0. Well, that means the fifth derivative will be also 1, the sixth derivative will be 0, the seventh derivative negative 1, and the eighth derivative would be 0 again. So that's what happens with these cyclic functions. In this case, like sine function, that's one of their properties. It's cyclic. It's cyclic of order 4 because that fourth derivative takes us back to the original function. Well, Maclaurin series f of x equals f of sigma n equals 0 to infinity, n's derivative at 0 over n factorial x to the n, and that's f of 0 over 0 factorial x to the 0 plus f f prime of 0 x to the first over 1 factorial plus f double prime at 0 x squared over 2 factorial plus, well, the pattern just continues, right? The order of the derivative with the power and the factorial in the denominator, the same number. Okay, so this is going to be f of x. So f of 0, which is 0 x to the 0 over 0 factorial plus 1 x to the first over 1 factorial, and then plus 0 x to the second over 2 factorial, and then plus negative 1 x to the third over 3 factorial, and then plus 0x to the fourth over 4 factorial, and well, plus whatever's next. So let's do some simplifications here. Number one, this couple of terms go to 0, and this one also goes to 0. That's going to leave us with the following. That leaves us with f of x equals, okay, I'm going to leave this x to the first power, but I'm going to leave this one in the denominator in factorial notation. I need this factorial notation to figure out the pattern for the power series. And then minus x cubed over 3 factorial plus, well, if the pattern continues, notice what do we have? Power 1, power 3, we have the odd numbers, 5 over 5 factorial, and then notice we have alternating them. Positive, negative, positive. The next one would be negative x to the 7 over 7 factorial plus x to the 9 over 9 factorial minus x to the 11 over 11 factorial, and so on and so forth. Alternate, and on top of that we have odd powers and denominators and factorial denominators. Alright, so let's figure out a pattern for this. Oh, that goes on forever. So f of x equals sigma n equals 0 to infinity. Of course we need some alternating factor, but we need to figure out the form of the factor. And well, so is negative 1 to the n going to be good enough? Well, so for n equals 0, negative 1 to the 0 power, yes, that's going to give us the positive term, the first positive term. Now we need to express x to some power over something factorial. Well, how do we express 1, 3, 5, 7, 9, 11, 13, 15, 17, etc.? 2n plus 1, that's the sequence of odd numbers, right? 2n plus 1, 2n plus 1. And that is the power series representation for the sine function. So one critical thing to connect the power series representation with the properties of sine. Do you notice the odd powers and the odd factorials in the denominator? Well, that means because this is sine, because sine is an odd function. So that's one of the reasons it's a pretty cool connection, right? So that's the series representation. Let's do the next one. And we call it a day. Find a Maclaurin series expansion for the function cosine x. And no, we're not going to do the whole process of finding four derivatives, evaluating. Actually, we're going to use the information that we got from the previous step. Well, so one thing to keep in mind is that the cosine function, so using calculus, the cosine function comes from taking the derivative with respect x of the sine function. Alright? But well, let's use the polynomial expansion from the previous example. And well, I'm just going to write a few terms. So dx x, let me write x to the first over 1 factorial plus minus x cubed over 3 factorial plus x to the fifth over 5 factorial minus x to the 7 over 7 factorial plus infinitely many terms. So let's take the derivative of this polynomial. General power rule. That's it. So the x to the first over 1 factorial, that's just x, and the derivative of x is just 1. That's just 1, and that's minus 3x squared over 3 factorial. But how about we write the 3 factorial as a 3 times 2 factorial, so we can simplify some coefficients, and then plus 5x to the 4th power over 5 factorial, which at the same time is 5 times 4 factorial, and then minus 7 x to the 6th power over 7 times 6 factorial, which is the same as saying 7 factorial, plus dot 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 infinitely many terms. And well, let's simplify this. Let's simplify some of the coefficients. 3 and 3, 5 and 5, 7 and 7. That's going to leave us with the following. 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial minus x to the 6th over 6 factorial plus the pattern continues x to the 8th over 8 factorial minus x to the 10 over 10 factorial. And then, well, before trying to figure out the general term of the series, how about we write this one as x to the 0 over 0 factorial. This way it would be a lot easier to see the pattern, because we're going to have 0, 2, 4, 6, 0, 2, 4, 6 in a similar way that we got the general representation for the sine function. We're going to do exactly the same for the cosine function. Sigma n equals 0 to infinity, negative 1 to the n, again because we need an alternating series, we need an alternating factor, and yes, the negative 1 to the n is going to work. And we're going to have something, x to the some power over parentheses factorial, something factorial. This time we're not looking at the sequence of odd numbers. This time we're looking at the sequence of even numbers. 0, 2, 4, 6, and that's correct. 2n factorial. Connection. What do we have? Even powers, even factorials in the denominator. That's because cosine is an even function. That's a pretty cool connection between the oddness and the evenness of the sine and cosine functions, and you can see them in its representation using power series.